Bismillah. Hello everyone. This is Gamal from your channel Think Math, and welcome to a new lesson. Today we are going to talk about functions and relations and the difference between them and some of the properties of functions. First, let's define a relation. A relation is something that relates two variables, like two numbers or two definitions, like it can be written as an ordered pair, like the relation between someone's name and his age. For example, if we say John and 7, he's 7 years old. We say Muhammad, 25, so we say that Muhammad is 25 years old, and so on. And it can also be written as a table or as a relation between two sets, like that. You can say, for example, name, age. So we say, for example, Ahmed, he's 5. Mike is 15, and so on. And we can write it like that. We have two sets, x and y. This is, for example, a set of numbers 1, 2, 3, and this is 6, 3, and 2, and we join each number with its image in the other set, and so on. Okay, so this is the relation between the x and y sets. And we can also represent this using graphs. So if we plot two axes like that, and we label them, for example, -1, -2, -3, 1, 2, 3, 4, and so on. This is the y-axis and this is the x-axis. So if you have the order pair when x is equal to 1, y is equals to 2, so we put a point here, and when x is equal to 2, y is equal to 3, when x is equal to 3, y is equal to 1, and so on. So this is a relation that we have been plotting on the coordinate axes. Okay. A special kind of relations is function. So a function is a relation when each number in the first set has only one image in the second set. So for example, if we have the ordered pair 2 and 3, the set of ordered pairs 2 and 3, 3 and 5, 6 and 1, so we can see that every value here in the first, which are the x's, is represented by only one value in the second one. But on the other hand, if we have these ordered pairs 2 and 2, 2 and 5, 3 and 4, so we can see that the number 2 has two images in y. The number 2 from the x has two images in y. So this is not a function. This is a relation and not a function, while this is a function. And it is also a relation because, as we said, that the functions are a special kind of relations. We can also, there is a test that's called the vertical line test, which we can apply to the graphs of relations to determine whether they are functions or not. Let's do this and apply it to some well-known functions. For example, if we have this plot, and we plot this function, like this is between a relation between x and y. If we plot any vertical line, any number of vertical lines, we can see that they intersect the graph of the function in only each vertical line intersects the graph of the function in only one point, like here, 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 and here. So this is a function. Okay, if we plot another graph, for example, if we plot this circle and we apply the same vertical line test, we can see that each line intersects the circle at 2 points. So that's how we know that the circle as a relation between x and y, it's not a function. Not a function because it fails the vertical line test. Functions are divided into two main categories, like the one-to-one functions and many-to-one functions. So in the one-to-one function, there is an additional test in addition to the vertical line test that applies to these ones. If it fails, then it is a many-to-one function. So like first let's say, what does a one-to-one function mean? Each value in x has only one image in y, and this is the definition of a function. But in a one-to-one function, each image in y has only one value corresponding to it in x. Okay, so this is one-to-one. Okay, for example, of the ordered pair 1 and 2, 2 and 4, 3 and 6, and so on. This is a one-to-one function. While the many-to-one function, like 1 and 2, negative 1 and 2, 2 and 5 and 4, and negative 2 and 4, this is a many to one function, because every value in y is repeated twice. Once with, for example, the 4 is repeated twice, once with the 2 and another time with the negative 2. How do we represent each one of these graphically, or how can we apply the horizontal line test? Let's, for example, make a graph for a one-to-one function. An example for this is the cubic function. This looks roughly like that. Okay. So if we apply the horizontal line test, it's like this. It crosses the graph at only one point, as you can see here. So each horizontal line here crosses the graph of the function at only one point. While if we plot a many to one function, and the famous example for this is any quadratic function which is represented by a parabolic shape, like this is the function y equals x squared. So if we make a horizontal line test, then we can see that each horizontal line crosses the graph at 2 points, so more than 1 point. This means that this is a many to one function. And we will, when we study later inverse functions, we know that functions can be inverted if they are only one-to-one functions. We have used the vertical line test to determine whether a relation is a function or not. But is there any other method? For example, if we have the equation representing the function or the relation, can we determine if it is a function or not? Yes, we do. For example, if we have y is equal to the square root of x. Okay, let's think of an example for x. Okay, let's take x is equal to 4. If we take the square root of 4, it has two values, positive or negative 2. So we have 4 and negative 2, and 4 and positive 2. So a value in x has two images in y. So this is not a function, this is a relation, this is not a function. For example, another example, y is equal to 3x plus 7. Okay, for one value of x, for example, if x is equal to 1, then y would be equal to 3 times 1, which is 3, plus 7 is equal to 10. So this is a function. Now let's talk about the function notation. So the function notation is the way how we write a function. Okay, so the function notation is sometimes written as f from x to x plus 3. This means that for every value of x, we add 3 to it. So an alternative way for writing this is writing f of x is equal to x plus 3. This means that for every value in the set of numbers that we are dealing with, we add 3 to them. Okay, and also if we use the x and y notation, we say that y is equal to x plus 3, or sometimes we say y is equal to f of x. Okay, so sometimes that we call x as an input. X is the input of the function and y is the output of the function, or f of x is the output of the function. Okay, sometimes we call the input, or x, as the argument, and f of x, or the output, is called the image. Okay, let's apply these function notations or rules to some examples. For example, if we have f of x is equal to x squared plus x. So let's find g of 2. Sorry, f of 2 and f of 3x and f of y. Okay, so let's apply this. Let's remove every x and put 2 in its place. So for the first one, f of 2 equals 2 squared plus 2, so it's equal to 4 plus 2, which is equal to 6. For the second example, for f of 3x, we take 3x and we square it and we add 3x to it. We remove every x and put 3x in its place. So it's going to be equal to 9x squared plus 3x. Okay, f of y, we remove every x and we put y in its place. So we say y squared is equal to y squared and plus y. We don't have to use x as sorry, we don't have to use f. Sometimes we say g of x, h of x, or even m of x. So all of these are just letters that we use to denote the function. Okay. Let's now define two important things related to the functions, which are the domain and range. What's the domain and the range? The set of all allowed inputs for the function is called the domain. So this is the set that we can choose access from. So the domain of the function is the set of allowed inputs or input values. Okay, we write the domain using set notation or interval notation or inequalities. Like if we use set notation, we say that the domain of x, the domain of f of x is R, which is the set of all real numbers. Or we can say x belongs to R. Okay? Or alternatively, we can say, if we use the interval notation, we say x belongs to from negative infinity to infinity. Or sometimes we write it like that. Some textbooks use this notation for the sets. This means that this is an open set from both ends, and this is an alternative way of writing that. Or we can say x belongs to z, which is the integers. So now we can choose for this function. We can say that x is can be any real number, but here for this one, x can be only an integer. One major difference between these two domains is that when we plot the first one, when x is a real number, we can plot it like that. It is going to be a continuous function. Okay. For example, if f of x, if f of x is equal to x plus 1. So when we write and x belongs to R, when we are going to plot it, it's going to be a straight line. It looks like that. But in the case of the same function f of x, x belongs to z. If we plot it like this. Is going to be a discrete function. It's not going to be a continuous function. So it's going to look like that. Okay. When we are dealing with functions, if no domain is explicitly mentioned, then we would assume that the domain is R, the set of all real numbers. Okay, but why do we ever need to have another domain? For example, in some functions we don't we cannot use negative numbers. For example, when you are dealing with real life applications of some of functions, for example, if we are dealing with the age of humans, so age cannot be negative. And there is no realistic age that's, for example, larger than 120. So our domain would be, we would say from 0, x cannot be to, for example, 120, for example. Okay, so this is our domain here. And if we write it in inequalities as an inequality, we can say x is greater than or equal to 0 and less than or equal to 120. The other main reason for having other domains than the set of real numbers is some mathematical operations are not defined at certain intervals. For example, if we have the function 1 over x plus 1. Okay, so we cannot have a 0 in the denominator, right? So x plus 1 cannot be equal to 0. So this means that x cannot be equal to negative 1, right? So that's why we say that our domain here is r minus negative 1. Okay? So when we are dealing with real functions, which are functions that are applied to real numbers or any proper subset of it, then we have three restrictions: that we cannot divide by 0, so the denominator cannot be equal to 0, and we cannot have a square root of a negative number, okay, and we cannot take a logarithm of a negative number or 0. Okay, for example, let's take a function f x plus 3. Okay, now we have two restrictions that we have mentioned. The first one in the first part is that we cannot divide by 0. So 1 over x minus 2, this is the first restriction. So x minus 2 cannot be equal to 0. So let's exclude the value that gives us x minus 2 is equal to 0, which is x is equal to 2. So we need to exclude this from our domain. And the other one is, the other restriction is from the square root. So square root of x plus 3. This cannot be a negative number. So x plus 3, we cannot be smaller than 0. So this is the other restriction, and we need to exclude it. So our valid values for x, or our domain, has to be x should be greater than or equal to -3, and x cannot be equal to 2. And if we write that in interval notation, we say that x belongs to the interval, closed interval from -3 to 2, and this is one is open, union the interval from 2 to infinity. Okay. Now let's talk about the range. The range is the set of all possible outputs of a function. Okay. Set of all possible outputs of a function. Okay, and the easiest way to determine the domain is to plot the function and find the values of on the y-axis that are images of values of the domain. For example, if we have the function f of x is equal to x squared plus 3. Okay. Okay, if our domain is x belongs to R, then let's plot this function and see what is the range. Okay, if we sketch this, the curve of this function, it looks like that, roughly. Okay. And this value is 3 here. And this is y is equal to f of x. Okay, so we can see that the range is y belongs to from 3 to infinity, or y is greater than or equal to 3. And if we restrict our domain to x is greater than 4, for example, if we say that this is the 4 value on the x-axis, then our range would be only, sorry, this part. Okay. Let's plot it on a different diagram better. Okay, our domain would be, sorry, our range would be like that. On here, this is 4, so this is going to be the range. This part of the on the y-axis. Now let's talk about piecewise functions. These are functions that do not have the same rule along all the values in the domain. For example, if we have f of x is equal to x if x is less than 0, x plus 2 if x is greater than 0, greater than or equal to 0 and less than or equal to 2, and x plus 5 when x is greater than 2. So we have 3 different rules for the function. This is called a piecewise function, and we can say that this function will have different plots in different parts of the domain. For example, let's sketch this a diagram for this function. When x was less than 0, f of x was equal to x, so we plot it like that. Let's do it in red. So, and here, since it's not x is not included in this range, we put it as an open circle. And when x is greater than 0 or greater than or equal to 0 and less than or equal to 2, it was x plus 2. So x plus 2 is, this is 2. Let's put that in blue. It's still a straight line, but it goes all the way until only x is equal to 2. Here is 2. Okay. Okay. And since both 0 and 2 are included in the domain, so we plot it as a closed circle. Okay. And when x is greater than 2, it was f of x was x plus 5. So x plus 5. So for x is greater than 2, it would be like here from, let's extend this line. So here from value of 7, so 2 plus 5 is 7, so it's going to be like that up to infinity. Okay, so now we can see that this function is not continuous. So a piecewise function can be continuous or can be discontinuous, but in our case here it's not a continuous function, and we are we can see this using this graph. Okay. The easiest way to find if the function is continuous or not is to sketch its graph. But if this is not possible, we can look at the values of f of x at the endpoints or near the endpoints of the different parts of the domain of the function. For example, if we have the function f of x equals 2x plus 1 when x is less than or equal to 2, and 7 minus x if x is greater than 2. So if we apply the rule of the function for the first part of the domain at the endpoint of the first part of the domain, which is when x is less than or equal to 2, so f of 2 equals 2 times 2 plus 1 is equal to 5. Okay, let's apply the same rule at the start of the other interval of the domain, which is here. Okay, let's apply this rule. So f of, let's apply it to 2, but let's apply 7 minus x, taking x is equal to 2. So 7 minus 2 is equal to 5. So we see that at this cutoff, or the boundary between these two parts of the domain, the value of f of x was equal from both ends. So this means that this is a continuous function. Okay, so that's it for today's lesson, and I hope you understood it well. And if you have any comments or questions, please feel free to leave them in the comment section below, and see you in next videos. Bye.